Okay, so here's the scenario you've got this meter stick right here, and it's clamped right in the middle at a position of 50 centimeters. Now the meter stick has mass, but it doesn't really matter because it's evenly distributed. So all the mass over here of the meter stick is the same as the mass over here, so it kind of cancels each other out. But what you have to be concerned about is the fact that there is a force over here that's causing the thing to want to tip in this direction, and then there's going to be a force over here that's causing it to want to tip in this direction. So this one makes it go clockwise, this one makes it go counterclockwise. So you want those to balance out. So where I think the problem becomes confusing is they say that 100-gram mass is hung at 20 centimeters. Well, that's 20 centimeters like on your meter stick. So that's really 30 centimeters away from the center of the meter stick. And then over here, it says, so how heavy is a mass that you hang over here that's going to balance at a position of 60 centimeters? So that's like a distance of 10 centimeters. So the equation says that all of the torques, if we're going to be in equilibrium here, rotational equilibrium, all of the torques that make it want to tip left have to be equal to the torques that make it want to tip left, tip right. So torque is force times distance. So you have force times distance over here has to equal the force times distance over there. And the force really here is the weight of the thing, which is going to be mass times gravity times distance equals mass times gravity times distance. So you can just kind of ignore the gravity, and you can have 100 times the distance from the point of rotation. It's always from the fixed point of rotation. Times 30 has to be equal to whatever that mass is times 10. So that's why this, sorry, that's 10. That's why this has to be 300.